So Santeri has been working on CMS and on Higgs analysis for nearly 10 years. He obtained his PhD from University of Helsinki in 2019, and he's currently working as staff research physicist at CERN. And the main research focus for him is in the recent years is di-Higgs searches, which are critical for measuring the Higgs self-coupling. Of course, like he's going to talk about the measuring the Higgs self-coupling. Yeah, I'll zoom over to Santeri, and you can start your talk.
Yes, thank you very much for the introduction and also for the invitation to come talk here about the Higgs self-coupling. In this talk, I'll try to cover a bit of the, let's say, motivate a little bit why we should be interested in the Higgs self-coupling in the first place, point out how it connects with the other topics that have been discussed here during the previous days, and also look a little bit towards the future. What can we expect in this front of Higgs self-coupling measurements in the coming years? As has been discussed during numerous nice talks here during the past few days, since the discovery of the Higgs boson 10 years ago, we have learned a great deal about its properties, and especially we have measured carefully its couplings to different standard model particles in the way that I think is nicely summarized in this plot here on the left. So we know a great deal about the way Higgs couples with the vector bosons, with the quarks, especially the third generation quarks. And as we heard yesterday, now we are also starting to reach towards the charm coupling, how it couples with the charged leptons. And also we have the first measurements of the Higgs to muon decays, which is also impressive, I think. However, after all this great work, there is one fundamental property of the Higgs boson that is still pending experimental confirmation, predicted by the standard model, but also, of course, in different forms in several BSM scenarios. And this is the property of the Higgs boson, or the Higgs field, if you want, to couple with itself, to interact with itself. And the standard model even predicts the strength of the self-interaction, so that measuring whether the strength of the self-coupling is exactly what the standard model predicts, or whether it deviates from that, would be another important test of whether the Higgs boson is really the one predicted by the standard model, or whether it is actually something else. So basically, any deviation from this standard model prediction would then indicate presence of new physics, and maybe would give us some hint about what type of new physics that could be. Okay, so in the following, we'll have a bit of a closer look to this concept of Higgs self-coupling. What do we exactly mean by that? And then we turn to look how it manifests experimentally at the LHC. And as you probably know, the most important experimental manifestation is the production of Higgs boson pairs. So I will spend quite a large fraction of this talk discussing our searches for these Higgs boson pairs in ATLAS and CMS experiments, and how the different search strategies there can complement each other in different ways. But then actually this is not just the direct searches for the Higgs pairs is not the only way to get information about the self-coupling. So then in the end, I will also talk a little bit about other ways to extract information on this based on all our measurements on the Higgs boson properties so far. Okay, so starting with the first question, what do we exactly talk about when we talk about the Higgs self-coupling? Something like this has been shown in the previous slides already, but I think it's a good recap here. So the standard model Lagrangian contains a number of different terms, and some of them determine the ways that the Higgs boson couples to other particles or their corresponding fields. For example, we have a certain term for the coupling between one Higgs boson and two top quarks. Then we have couplings with a vector boson, such as one Higgs boson and two vector bosons, or even two Higgs bosons and two vector bosons, etc. And then regarding the self-interactions, we have two interesting terms here, which are the red one and the orange one, corresponding to the so-called trilinear Higgs self-interaction here, and the quartic Higgs self-interaction here on the right in orange. Now, in the standard model, the strength of these two interactions, the trilinear one and the quartic one, are actually essentially the same. So we can just mark them as a common coupling parameter lambda. And the standard model even predicts the exact strength for this coupling, determined by the mass of the Higgs boson and the vacuum expectation value of the Higgs doublet of the standard model Higgs sector. However, as I mentioned in the beginning, so far this is just a theoretical statement, since we have not yet been able to nail down experimentally, first of all, whether this trilinear and quartic self-couplings actually agree with each other, and secondly, what is the exact value of this coupling. So, of course, this is an interesting thing in itself, this question whether the value of the coupling agrees with the standard model prediction. But what is also interesting is that the value of the self-coupling has, I would say, major consequences also in the larger picture of the Higgs sector and the electroweak symmetry breaking. So here is the classic Mexican hat potential, the shape of the Higgs potential as predicted in the standard model. And here is also the equation for that. And you see that these self-coupling terms enter this equation that determines the shape of the Higgs potential. So in other words, measuring the self-coupling will directly give us information about the shape of the Higgs potential. Second of all, it's not clear that that the shape of the Higgs potential would be exactly as the standard model predicts. And in different BSM theories, you open up possibilities for different, let's say, different shapes of the Higgs potential in the sense that it's not guaranteed that the current minimum of the potential where we expect to exist at the moment would be the global minimum of this potential, making it a stable situation. But also there would be the possibility that actually we live in a metastable universe, and the Higgs and the minimum of the potential could actually at some point shift to an even lower state. So therefore, studying the self-coupling and trying to understand the shape of the potential, also, I mean, not just in the context of the standard model, but also in this wider picture, is extremely interesting. Okay, so then I hope this motivates a little bit why we should pay attention to this Higgs self-coupling. So let's move on to discuss the experimental manifestations of that at the LHC. And as I mentioned in the beginning, the most important manifestation of that, in the sense, is the presence of the di-Higgs production, so production of Higgs boson pairs at the LHC. And usually these two things are kind of discussed together. It's very hard to discuss about the self-coupling without talking about the di-Higgs production. And on the other hand, it's impossible to talk about the di-Higgs production without taking into account the self-coupling that regulates these di-Higgs production processes to a large extent. So the first thing to point out is that this di-Higgs production is an extremely rare process at the LHC. there have been a long-standing theoretical efforts starting already in 1980s to calculate the cross-sections for these different Higgs production modes. And the precision of these calculations has been improving drastically over time. And when you put all this information together that we have, you end up with an inclusive cross-section for the Higgs production that is roughly 1,000 times smaller than our inclusive Higgs production cross-section. So experimentally, now that we are celebrating here the 10-year anniversary of the discovery of the Higgs boson, at the same time we are now setting ourselves to chase for a process that is literally 1,000 times more rare, at least if we trust the standard model prediction for this process. Then, of course, if we have some new physics entering the production processes, then this could be enhanced considerably compared to this prediction. So this is just based on the standard model. Now, what this means in practice is that at the LHC, when we are running, we approximately produce 1 Higgs pair per hour, as compared to producing roughly 1 Higgs boson each second. And this means that the total number of Higgs pairs that we have produced so far, for example, during the run 2 of the LHC, let's say in the CMS, is only roughly 4,000. So we are talking about relatively small sample of events that we would like to be able to identify and use in our experimental analysis. So then looking a bit closer to the different production modes of these Higgs boson pairs, here you have this cross-section plot in the logarithmic scale, and the current 13 or the upcoming 13.6 TV cross-section is here on the left, and then the scale reaches out all the way to the potential FCC collision energies of 100 TV. But you see that the hierarchy between the different production modes remains more or less the same. So the dominant production mode by far is the gluon-gluon fusion, where then this Higgs self-coupling enters, as you see in the Feynman diagram here, enabling the Higgs production via GGF. And then the second largest production mode is the vector boson fusion, even though you see that it is already an order of magnitude smaller than the GGF. And these are basically the 2 production modes that we have been actively looking for experimentally, for the gluon-gluon fusion already since the LHC run 1, and for the vector boson fusion, more active efforts with dedicated event categories for the VBF events have been involved in many analyses now during run 2. Personally, I would assume that the next logical step, probably for run 3 analysis, or maybe even some legacy run 2 analysis, will then be also dedicated categories for this TTHH or BHH production mode, because eventually, of course, we want to be able to maximize our total sensitivity. And also these different production modes give a slightly different type of useful information on the Higgs production. Okay, so this is the production mode summary as predicted in the standard model. But now we can look a bit what happens if we relax the assumptions that all the couplings, which I mentioned, which are there in the Lagrangian, are exactly as predicted in the standard model. And for this, now I will just focus on this gluon-gluon fusion production mode, which is by far the dominant one, and therefore now here serves as an example of how these deviations from the standard model can manifest. So as presented already in many of the previous talks, we often use this so-called kappa framework to parameterize the deviations from the standard model. So here is the standard model coupling, and then we add a free parameter, for example, kappa T for the Higgs top coupling, or kappa lambda for the self-coupling, to parameterize the deviation from the standard model value. So for these kappas, number one always, value of one always corresponds to the standard model coupling, and then any deviation from one is an indication of presence of some BSM physics. So now looking at the gluon-gluon fusion, we have actually there two diagrams contributing to this process. One is the one that I showed already on the previous slide.
Could you kindly tell me why they are appearing in the Lagrangian with opposite signs?
Right. I think this is probably just a matter of convention, and I don't think it. I mean, it doesn't drastically change the argument here.
Sure. Okay.
Okay, but yeah, that's an interesting question actually. Why there is a minus here? But I think it's simply a convention. Yes. So the one diagram is the one that I already showed on the previous slides with the self-coupling, and then also the top Higgs Yakava coupling entering here. And then the other is the so-called box diagram regulated by this top Yakava coupling squared because it enters here in two places. And now both of these diagrams contribute, and actually they interfere with each other. And the results you can see here. So this is now showed as a function of the di-Higgs invariant mass, the invariant mass of the di-Higgs system, which is a very important variable to understand this di-Higgs production, and which we will encounter here many times. And as you see, this triangle term with the self-coupling has the largest contribution actually at the very low values of the di-Higgs invariant mass, whereas this box diagram then peaks here a little bit later. Then we have the interference term here on green, and then when we take all of these into account, we end up with this total prediction for the differential cross-section as a function of MHH, which is shown here on the black. And this means that by probing the shape of this MHH distribution, we can actually gain information on the relative strength of these couplings. The example here is shown, of course, for the standard model values of the couplings, but then if we would vary them, either the kappa lambda or the kappa t here from its standard model value, then actually the shape of this overall distribution would change accordingly, and this is something that we could try to measure experimentally. In addition to this, also, of course, then the total, not just the shape, but also the total cross-section changes depending on how large this interference is. So then when we do this exercise and we look at the total cross-section as a function of this kappa lambda modifier for the self-coupling, for the different processes, the GGF is here in gray, and then the other ones follow here with the lower cross sections. And you see that there is quite an even dramatic dependence somehow on the cross section on this strength of the coupling modifier. So this means that if we can set limits on the rate at which we produce Higgs boson pairs, then we can interpret it as a limit on the strength of this self-coupling. And then if we can actually get our hands on this differential distribution of the di-Higgs invariant mass, then we have even a more powerful handle to obtain information from the value of this self-coupling.
Santeri, I have one more question.
Yes, please.
Could you please tell me why what do the dark and the lighter bands correspond to in this bottom block?
Right, you mean here on the top?
Yeah.
Yeah, I think this is a good question. Because
okay, fine. Let's go on. Fine.
Yeah, we should double check.
Yeah. Now,
What's the exact difference between the two?
Isn't it like the LO and NLO?
Right, so that you're saying that the dust would be without the loop corrections and then the
Yes.
solid would be with the corrections.
Yes.
Yeah, I think that's a good guess indeed. Yeah. Okay, good. I think that's it, but I mean, for sure, we can look this up and double check that. That's really it. Okay, yeah, but I mean, the message, the main message I wanted to pass here is just that you have this clear dependence on the value of the coupling modifier, which means that this di-Higgs production, even via GGF, which is the dominant mode, then gives us access to this self-coupling. Okay, so then the next question, of course, is how can we probe this di-Higgs production experimentally? With many of the single Higgs results talk, you have already seen this chart of the branching fractions for the Higgs boson decays. And now then, of course, with two Higgs bosons, we can do the math to get the overall branching fractions for the Higgs boson pairs in all the different possible combinations of the final states for the two Higgs boson, and we end up with a table like this. And here, experimentally, it's not very clear what would be the best channel or the best approach to start hunting these di-Higgs pairs and nailing down the coupling. Because basically what we have here, as it's written here, we have a trade-off between a mode such as di-Higgs to 4b, which has a very large branching fraction, but also an overwhelming background from the QCD multijet production, because we are talking about a fully hadronic final state here. Then on the other hand, for example, we have the final states with a Higgs to gamma gamma or Higgs to ZZ decays, which we know they are experimentally very clean, and we have seen in the previous talks that with the single Higgs measurements, these channels are extremely competitive thanks to this cleanliness of the final states. But then if we would choose both Higgses to have these decay modes, then our branching fractions would be so negligibly small that we would not have essentially any signal in our run-2 dataset. So then we need to make some compromise, and usually we always select one Higgs to decay to BB, and then we scan over the other decay modes for the other Higgs. And traditionally, meaning since run 1, looking at the Atlas and CMS results with all these different final states, the most sensitive top 3 decay channels, for which it's very hard to put them in the order of which one would somehow be the best one, are usually this 4B with the largest branching fraction, BB gamma gamma, thanks to it being very clean, as I will explain in more detail a bit later. And then surprisingly, BB tau tau as a good compromise between these two. So still a reasonable branching fraction, but also much less QCD background than in the 4B final state. Over the past few years, basically always when CMS or Atlas puts out new result in any of these channels, it tends to be, slightly more competitive than the other results until some other channel puts out the next result. And there's been like an ongoing competition between these 3 channels for the long time. And it's not clear which one would somehow, if there would be in longer term some clear advantage with one of these, or whether they will just keep going more or less hand in hand like this. Now here is one snapshot of the situation from the CMS combination with the 2016 data, where you see that in that case, for example, the BB gamma gamma was the strongest one in terms of the expected limit, and also in terms of the observed limit, but then the BB tau tau was there right behind. And of course, the nice thing about these different final states is that we don't have to choose just one of these. But of course, what we want to do is we want to do this all analysis. We want to do them so that they are statistically independent, so that in the end we can just combine them to get the maximally sensitive maximal sensitivity for the Higgs production. And here is an example of how that worked out in 2016 in CMS. Okay, so before moving on to discuss these different experimental channels in more detail, I just wanted to point out that, of course, just as in the case of single Higgs hunting, also the double Higgs hunting is really a community effort. Of course, it relies on the huge amount of technical work with the collider, with the experiments, etc., to keep things running and to keep the data coming. But also in terms of the actual, let's say, Higgs community of theorists and experimentalists who actively work on this subject. This is several hundred people around the world at the moment. Last week, I had a privilege to be in Dubrovnik, Croatia, meeting roughly 100 of Higgs enthusiasts, both theorists and CMS and Atlas colleagues in person. This was a hybrid workshop with also wide online participation from around the world. And this was really the first time this community was together since a few years ago. So this is a rare opportunity to actually show you some of the faces behind the results that I am going to present in this talk. Also, the amount of results that we have, just the experimental results from Atlas and CMS, is already very large. And in an anniversary seminar like this, it would be nice to be able to make justice to every one of each analysis that has contributed to our understanding, but unfortunately, the number of results is already so large that it's basically impossible. So what I will do in the remaining of the talk, basically during last week in the workshop, I picked a bunch of results, recent results from Atlas and CMS that I consider to be somehow the most relevant or most interesting, maybe also with some personal bias. And I will just focus on them. And then if you want to get the full picture, I really welcome you to go see the workshop agenda and all the talks in there and all the results presented in those talks. Also, actually, some of the results that I will mention are very recent. Atlas made public some new results just for this last week's workshop. So they are kind of fresh out of the oven also for today. Okay, so then we can move on to discuss the main features of these top 3 most sensitive final states that we can use to probe Higgs production. The first one is the BB gamma gamma. Here is a nice event display from Atlas with 2 B jets and 2 photons reconstructed in the event. As I mentioned, the branching fraction is small, but this final state has some major benefits, which are actually the same ones that we have in the case of single Higgs to gamma gamma. So first of all, we can trigger and reconstruct these photons very efficiently, even at low PT, where, for example, our jet triggering or jet reconstruction is not at its best, meaning that this BB gamma gamma channel gives us access to this low MHH part of the spectrum, which, as we discussed a bit earlier, is the one where this Higgs self-coupling contributes the most in the standard model. And then experimentally, of course, the most appealing feature of this final state is the excellent energy resolution of photons. So here you can see from a CMS analysis a comparison of the signal peaks for this Higgs to gamma gamma decay on the left and Higgs to BB decay on the right. And if you compare the width of the peak, you can see nearly a factor of 10, I would say, maybe a factor of 8 or something difference in the resolution. And this, of course, then translates directly to signal to background ratio and therefore to the analysis sensitivity. Okay, and then a bit similarly to what we do with the single Higgs to gamma gamma analysis, also here we can perform the background estimation with the help of these parametric fits. in the sidebands of data. The extra challenge that we have in this BB gamma-gamma channel now, compared to the single Higgs case, is of course that the single Higgs to gamma-gamma actually enters as a background in this analysis. And therefore, both Atlas and CMS have trained dedicated multivariate classifiers, either BDTs or DNNs, to discriminate between the single Higgs signal, which you can see on yellow peaking here on the left, and the di-Higgs signal, which you can see here peaking at the higher Tagore scores. And here is a similar case for the CMS, where there is a specific discriminator to reject the TTH background. Since the B jets from the top decays make this kind of the major problem when it comes to these single Higgs backgrounds. Okay, and here you have a couple of nice plots from the CMS, again showing how the energy resolution of the photons helps us to form something of a visible signal peak here around 125 GeV, whereas for the Higgs to BB, it's very hard to see anything there, at least with a plain eye. So then we can move on to compare the results of this BB gamma-gamma channel from the Atlas and CMS. These are both now with the full run-2 dataset, as everything else that I will be showing today. So there are usually, the way we present these results is to set a limit as a function of this strength modifier of the self-coupling, setting all the other Higgs couplings to the standard model values. And then we can compare the observed or expected limits with the theory cross-section, which is here in the red, and which depends on this parameter, just the way I explained a few slides ago. And then the crossings of this theory curve and the observed upper limit for the production cross-section give us the experimental constraint for this kappa lambda parameter, and therefore for the self-coupling. And here on the plots, I always overlay the constraints that we get. In this particular case, you see that the sensitivity seems to be pretty much comparable with the slightly stronger constraints from Atlas, and especially this upper limit of 6.7 for kappa lambda that we get from this crossing is actually the strongest one so far by any single analysis from Atlas or CMS. Then another key number that we usually want to look at is the upper limit on the standard model cross-section. So if we take kappa lambda to be 1, how far is the observed limit here from the theory prediction? And here you can see that for the Atlas, it's a factor of 4 away, whereas for the CMS, it's a factor of 8, more or less. But the expected limits are comparable, so it's just a matter of having a slight over fluctuation or under fluctuation in the data. And now this number is, of course, interesting because ultimately we would like to be able to reach the precision, the sensitivity to probe even the standard model process, and therefore this is the number that we want to push as close to 1 as possible. Okay, so that's it about the BB gamma-gamma. Then we can move on to the BB tau-tau, which here we have again a couple of nice event displays. This one is from CMS. And here is one from Atlas. I think here the blue ones are the B jets and the red ones are the 2 hadronically decaying tau leptons. And as I mentioned, this BB tau-tau channel can be understood basically as a good compromise between the efficiency or the branching fraction and the purity in terms of the background rejection. Now, the main challenges here are, again, actually pretty similar to what you have in the single Higgs to tau-tau analysis. So the main task which directly affects the sensitivity is how well you are able to reconstruct your tau leptons, and of course, especially the hadronic decay modes are the tricky ones, because there usually what happens is that you end up with a mixture of hadronic signatures from the charged pions and then electromagnetic signatures from the decay of the neutral pions. And in the identification of these hadronic tau decays, actually even in the recent years, there has been a lot of development in both experiments. And for example, in the CMS, we are now benefiting from this new deep learning approach using low-level inputs, which is known as the deep tau algorithm. Here is one example of how this new deep tau algorithm performs in terms of the efficiency to identify the true taus and to reject background from jets misidentified as taus. And we see that the background rejection is improved at least by a factor of 2 per tau candidate with this new algorithm compared to the previous ones that we used in early run 2 or even run 1 analysis. And if this is a factor of 2 per tau, then of course with Higgs to tau tau, then that should be already a factor of 4 improvement, which is quite substantial. Now, usually these analyses also include the channels where one of the taus decays hadronically and then the other decays leptonically, so that you have a muon or electron in the final state. But in most cases, the sensitivity is driven by this channel with 2 hadronic taus. Okay, so then the other aspect of these measurements is the background estimations, where usually both experiments follow the approach where the genuine tau backgrounds, which are somewhat well understood in simulation, are taken from simulation, but then dedicated control regions are included in the fits to constrain the systematic uncertainties and the normalization for those backgrounds. Whereas then another important background component, just as in the case of single Higgs to tau tau, is then these misidentified taus, so-called fake taus, which are mostly QCD jets misidentified as hadronic taus. And this background is very tricky to get right from the simulation. So basically in all the analysis, what you do is then you develop some data-driven estimation method where you define a control region enriched in these QCD multi-jet events, and then you normalize that background contribution to your signal region. And also, as is case with the most analyses that I will be showing today, also for this BB tau tau analysis, both experiments are now using multivariate classifiers to discriminate between the signal and the background. Here is the BDT from Atlas, where you can see the nicely enhancing signal contribution towards the higher values. And here is a DNN from CMS, where actually here the signal looks more or less flat, whereas the background is going down considerably as we go towards the higher values.
Santri,
yes.
May I ask a question? So how these beams were defined?
How are the bees?
No, the beams. The beams.
Ah, the beans. Right. That's a good question, because usually, and I think maybe this is even what prompted the question, usually the more aggressively you bin your discriminator, the better sensitivity you get, right? So then usually, I think there are slight differences between the analyses, but usually the way you define the final binning when you extract the signal is that you set some minimum number for the background events or the simulated events that should enter every bin. And then you also set some maximum allowed statistical uncertainty for the overall background contribution in each bin. And for example, looking at these plots, to me, it looks like CMS here is binning slightly more aggressively than Atlas. but I would assume they are both using some predefined criteria to determine the binning. It should not be just arbitrary. Does this answer the question?
Okay, yeah.
Okay, thanks. Yeah, but I mean, these are certainly exactly the type of things that you need to pay attention in the analysis design, and which directly affect the sensitivity. Okay, so then we can take a look at this.
Yeah, a reminder.
Yes. Sorry, can you repeat?
20 minutes left.
Okay, yeah, thanks for letting me know. Okay, so then we can take a look into these BB tau tau results from both collaborations. And again, it's the same thing. I'm overlaying here the constraints that we get for kappa lambda. And they are also, in this case, fairly comparable. It's nice to see that even though the details of the analysis are always pretty different between the two experiments, then the differences often cancel out in the sense that in the end you end up with more or less similar limits. And then if we look at the upper limit for the standard model Higgs production, here it's interesting that actually the atlas has a slightly stronger expected limit, and I think this is actually the current best expected limit from a single analysis for the standard model Higgs production. But then CMS actually has a stronger observed limit because of the slight downward fluctuation in data. So I think this just shows that the two experiments in most channels are so close to each other in performance that it's mostly a matter of getting lucky with the data that you have in the end, whether you have some fluctuation upward or downward, which determines your final result. Okay, so then we can move to the third of these, let's see, traditional top 3 most sensitive channels, which is the Higgs to 4b. Now here is again a nice event display from Atlas with 2 B jets coming from one Higgs and 2 others from the other one. And then actually on the cover slide of the presentation, I have a similar picture from CMS with the 4 B jets as well. So as I mentioned, the main benefit, of course, here is this very large overall branching fraction, 1/3 of all Higgs pairs. But this comes with the price of the large QCD multijet background. And then another major challenge here is resolving the jet combinatorics. So usually you have a large number of jets in your event, not just 4, but maybe even a 10 or something. You need to be somehow able to identify which one would be the most likely to originate from the Higgses, which you usually do by B tagging, of course. But then even after the B tagging, it's still the question of how you pair these, let's say, 4 B jet candidates correctly to form the 2 actual Higgs bosons. And a lot of development has been going in both collaborations to this method of solving the combinatorics in the best possible way. And actually now both Atlas and CMS have, at least for the standard model Higgs case, they have more than 90% correct matching efficiency to pick the right jets and pair them correctly in these events. Now, since this background is mostly QCD multijet, and I already mentioned it's not really possible to get it right from the simulation, then another key area of these analysis are the data-driven background measurement methods, which would give you as accurate background estimate as possible with as small systematic uncertainties as possible, because here then the systematic uncertainties on the background really start to be the limiting factor of the measurement, because I mean, for once we are not really so limited by the statistics, so then it's mostly the question of nailing down our background estimate. And also here, I would say a lot of innovation has been taking place in both collaborations. And now both Atlas and CMS are using pretty advanced machine learning based methods where they select a QCD enriched sample and then they actually train a BDT or a DNN to reweight those events in such a way that it corrects for the differences in all kinematic distributions that you use in the analysis, so that after the reweighting, the background sample behaves in the same way as the background should behave in the search region. And usually what they do, here is a plot from CMS, here from Atlas. Usually what they do is they define the so-called signal region or search region in these circles or areas where both Higgs candidate masses are close to 125 GeV, as you would expect. And then they define a number of control regions and validation regions in these different mass sidebands around the search region to select these background-enriched samples to perform the reweighting with the machine learning methods and to validate it. Yeah, so these techniques, I think they are quite interesting. I hope they will be used in other analyses as well in the future. They would be maybe worth their own seminar, but I just want to point out that this is, I think, a critical area in this 4B analysis. Okay, and then after this, with the B tagging pairing of the jet and the QCD background estimation, usually what you also want to do is you want to apply again some multivariate discriminator to suppress your QCD background as much as possible and to extract the signal. And then this way we again arrive in the results from both collaborations. Was there a question? Okay, I don't hear a question. Yes, so here again we have the comparison of the results. Starting with the upper limits on this standard model case. Now you see that actually this time both Atlas and CMS got lucky, and we have slightly stronger observed limits than the expected ones. But then when we look at these kappa lambda constraints, then the results look more or less comparable. But one thing to point out is that I think this lower limit of -2.3 that we get from this crossing here from CMS, I think it's the best lower limit from a single analysis for this kappa lambda so far, unless I'm forgetting some other analysis. Yeah, so looking at these results from the different channels, what we see is that first of all they are fairly comparable, and second of all, each of them brings something new to the table in the sense that somebody is able to constrain the kappa lambda a bit better from upwards or from downwards, or set a slightly stronger limit to the standard model cross section, etc. So indeed, these results work best once and when eventually we will be able to combine all of them and squeeze everything out from each channel. Okay, so then before moving on to other final state, I just wanted to highlight that talking about the di-Higgs to 4B, we also have, let's say, a new kid in town. So another approach to perform analysis in this 4B final state, which was just recently done for this non-resonant di-Higgs search for the first time by CMS. I would assume that our Atlas colleagues are working on a similar measurements, and maybe we will hear from it later. But let's see a little bit what do we mean by this boosted di-Higgs to 4B search. So here the idea is to target the small fraction of these di-Higgs to 4B events where the Higgs bosons, both of them have such a high PT that the two B quarks that we get from the Higgs to B decay get so collimated that actually we can reconstruct them as a single large radius jet that contains these two B quarks inside the jet. This is a bit of a similar idea than what you saw at least yesterday in the talk by Lukas Guskus about the Higgs to charm analysis, where you also have this boosted category where the Higgs decays to 2 charms which are contained inside a single jet. And now, of course, the price to pay here is that it's a tiny fraction. It's just a few % of all these di-Higgs to 4b events that actually are in this very high PT region, so that this is the case. But on the other hand, even though we lose a lot of statistics, all the other usual troubles with this 4b analysis gets mitigated a lot, let's say. So first of all, we don't have any more these combinatorics of 4 different B jets, because we only have 2 large jets, and it's clear that one corresponds to one Higgs boson and the other one corresponds to the other Higgs boson. Secondly, having the both B quarks inside the single jet actually helps with the B tagging, or in this case with the double B tagging, because now we can fully exploit all the correlations between these 2 B quarks and the way they manifest in the jet substructure, the secondary vertices identified close to those jets, etc. And thirdly, since now we are in this very high PT tails of the distributions, also, of course, our standard model background, and most importantly, the multi-jet QCD background is reduced just because it's exponentially falling as a function of PT. All of these things combined, they kind of balance out the fact that we are only using just a few % of our signal events in this 4B final state. And the idea is that we use these few % of the events very efficiently. Now, how we do that? Here is just a rough sketch of the idea of the analysis. So eventually, what we aim to do is we aim to look for a Higgs signal peak above this smoothly falling QCD multi-jet background, which we estimate with a data-driven method using a QCD-enriched background region to get a sample of these QCD events. And this is also shown in practice here, where on the left you see this QCD-enriched control region. This is in the logarithmic scale, so actually the QCD contribution here is completely overwhelming. And then on the right you see the signal region, where we have a mixture of different backgrounds. The other ones are coming from simulation. And then we have actually here around 125 GeV, a small hint of a possible di-Higgs signal shown as the red contribution here. So now with this strategy, the 2 main tasks that basically determine the sensitivity of this analysis is, first of all, how well can we suppress this QCD multi-jet background? And secondly, how good resolution can we get for our signal peaks? So basically, what is the mass resolution of these large radius jets that we use as our Higgs candidates? Starting with the first question, how well can we suppress the QCD multi-jet background? Here, the main handle to do this in this analysis is this double B tagger algorithm. And actually, this is one of the first analyses in CMS and in general that use this novel particle net GNN tagger. This is the same one that was used in the Higgs to charm analysis presented yesterday, which has a background rejection improved by a factor of 2 compared to the previous best algorithms, such as the deep AK8. So then with the 2 Higgs jets in the event, this means a factor of 4 background rejection compared to the previous algorithms. And this tagger is trained in such a way that it does not sculpt the mass of the jets. So our smoothly falling QCD background remains as a smoothly falling background even when we apply this tagger. And this is an important aspect from the analysis point of view.
Yeah, 5 minutes left.
Yes, thanks. And then just to mention, for the other challenge, which is the mass resolution for our signal peaks, also here we can use the same particle net graph neural network architecture to improve our jet mass prediction compared to the previous best mass grooming algorithms, which gives us something like a 20% sensitivity gain in the analysis on top of the other improvement that I mentioned on the previous slide. So now putting this together, even given the fact that we are just using a few percent of our Higgs to 4b event in the very high PT tail of the distribution, the result that we get from this boosted analysis is quite competitive, actually. Especially if you look at the, here we have again the kappa lambda constraints, and then if we look at the limit on the standard model cross-section, here you see that with the observed limit, we got a bit unlucky with the upward fluctuation, but the expected limit is roughly 5 times standard model, which is actually the best one that we have among the current CMS analysis. So here you have a comparison of all these different analyses. Now I have discussed the 4B result, BB gamma gamma, BB tau tau, and here is the new boosted 4B channel with the strongest expected limit so far. So this, I think the takeaway message here is that even by using a very small sample of events, which otherwise would have been just a few percent of the overall signal in this 4B resolved analysis, if you can make an efficient use of those events with the new innovative techniques, then you can actually, you might be able to still achieve a competitive result, which also can be still in the future, can be still combined with all these other channels so that the overall combined sensitivity will further increase. Okay, so then I only have a few minutes left, but I just wanted to quickly flash you that even though these are the top 3 final states that we usually focus on, of course, we don't want to leave any other stones unturned. So we also have analysis targeting these remaining WW and ZZ final states with the BB. And then we also have a so-called multi-lepton analysis targeting these combinations of Higgs to WW and Higgs to tau tau decays with a number of electrons, muons, or hadronic taus in the final states. I have here a few slides with the results. I will not go over these in detail because, as you will see, in all cases, the sensitivity is not really comparable with a few analyses that I showed earlier. But I think these are very interesting efforts, each of these, and so I wanted to include them. So you are welcome to take a look if you want, and also you always find the link to the full documentation from the Atlas and CMS. So here we have the Higgs to BBZZ. Here we have the Higgs to BBWW or ZZ or tau tau from Atlas. And then finally, here we have the CMS Higgs multi-lepton analysis, which is the only one without B's in the final states among the analyses that I present. And the upper limits are around 20 to 30 times the standard model cross-section for all of these. Okay, so then the last word about the Higgs is, of course, that it's very interesting to think how well can we do in the future. Here is one projection which is already a few years old. You can find the link to the full documentation here, which back then projected that we would obtain a 4 sigma significance for the standard model Higgs production with the full high Lumi LHC dataset. Now, my personal judgment would be that already since this prediction was made, there has been a huge improvement in experimental techniques, most of which is not reflected in these results. So I would take this as a very conservative estimate of our future potential at the moment. And therefore, if even with a conservative estimate you end up with 4 sigma, then my personal judgment would be that crossing even the 5 sigma threshold with all the existing and the upcoming experimental improvements, I think should be a completely realistic goal for us to set. So that's promising. Then the last couple of minutes I want to spend just by quickly pointing out that actually the Higgs production is not the only way to obtain information about the Higgs self-coupling, but it also enters the single Higgs processes at the loop level. Here are a few examples of these loops with a single with the Higgs self-coupling. Either with this kind of generic loop where it enters twice, or then for the different production mode, TTH, or the VBF, or the Higgs with the vector boson production, where you always have one Higgs self-coupling vertex here regulating these processes. And then if you do the math, you will find out that this means that this value of the self-coupling actually through these electroweak corrections affects both the production cross-sections of the different single Higgs processes and the branching fractions of Higgs bosons to different final states. So therefore, we can use just this, all the measurements that we have on the cross-sections and branching fractions, as well as information, for example, on the STXS cross-sections, just to make a connection to the previous talk, to extract information on this self-coupling. Now, and these type of studies have been carried out. Here are the most recent results from Atlas and CMS. Here is the list of all the input analysis that went into this study. And you see that the limits that we get for the value of the self-coupling, here from -3 to 12 and here from -4 to 15, are actually quite competitive with respect to the Higgs searches that I just presented earlier. The Higgs searches are slightly better in most cases, at least the most sensitive channels at this point. But it's surprising how much you can do already with this, also with these indirect methods. And now, as the last thing, of course, eventually, also we don't, just as we don't have to put the different Higgs channels to compete with each other, also there is no point of having a competition between single Higgs and Higgs measurements. The ultimate goal, of course, should be a global combination of all these single Higgs and Higgs results, so that we can get the full benefit from all these different constraints from different final states. And this would also enable not just scanning kappa lambda and setting all the other couplings to their standard model values, which was the case for all the results that I showed so far, but this would enable more global, let's say, multi-dimensional scans of various different Higgs coupling modifiers for the Higgs production, for the single Higgs production, etc. And of course, also EFT interpretations going much beyond this simplified kappa framework that I've been using to discuss the topic in this talk so far. So I think in a longer term, this is certainly the direction where we're heading. And this brings me to the summary slide. Since I'm already a bit over time, I think I will just leave the summary here and we can use the remaining few minutes to discuss if you have any questions or comments. Thanks.
Yeah, there seems to be one question. Thanks a lot, Santeri, for summarizing the self-coupling results from both Atlas and CMS. And there is one question from Soumya. Soumya, if you can unmute.
So, yeah, my question is that how you were just remove the overlap between the boosted and resolved Higgs to 4B analysis, because finally you were combining. So hopefully yes, there is no overlap between them. So are you putting any cut on the fat? I mean, the large radius Z transverse momentum like 300 GeV or so? Or?
Yes. So this is, I mean, this is indeed something, eventually when we want to combine all these different analyses, we need to resolve the overlaps between all of them. And it's true that since we have now two analyses in this 4B final state, it's a bit less evident what is the optimal way to, let's say, to split the phase space between the two analyses. And we carried out actually a number of studies exactly to understand these points and understand which division would give the best combined limit. And basically the outcome was that because this merged jet boosted analysis is, as I said, it's only using a few percent of the full signal phase space that is targeted by the resolved analysis. If the resolved analysis vetoes the events that contain these boosted jets, the sensitivity of the resolved analysis does not suffer that much because they are just basically like cutting away a few percent of the whole phase space. Whereas for the boosted analysis, we are already very limited in statistics, and therefore if the boosted analysis would start vetoing some additional events for the sake of combination, this would very easily then eat out the sensitivity that we have there. So the outcome was that basically the boosted gets the priority in this case, just by this argument that it's a very tiny fraction of the whole phase space, but we use it very efficiently.
Oh, okay, thanks. Yeah.
Okay, thanks, Santari, once again. So let's